Kevin Phillipson. We're both students from the University of Florida. We're not young students though. We're
a little older.
Yeah. So we both decided to work on for our masters. We both decided to do a thesis on a common project. What I'll be presenting today is my master's thesis. So I'll be doing most of the talking. So this is my master's thesis defense, but there'll be some crossover with Mike, and so he can comment on a few slides. Also, we work with Boise, so I'll make him say a few words occasionally. But yeah, let's go ahead and get started. I would like to say one thing before we start. So I was thinking about editing this and make it a little more CoCo specific, but I decided against that. I wanted to give you the straight master's thesis defense. So this is going to basically be a lecture on the microprocessor design. And I'll stop at certain points and talk about some CoCo related stuff. But this is going to be pretty much what I presented for my master's thesis defense. But the title of my master's thesis was a compact and efficient microprocessor IP for SoC subblocks and mixed-signal ASICs. These are the esteemed professors that were on my committee. And like I said, my name is Kevin Phillipson. My project responsibilities were the microarchitecture design, the RTL and microcode development. I am a IC design engineer. That's my profession. I've been working in the industry for about 13 years. I now have a master's. I graduated this semester, so I have a bachelor's from the University of Florida in 2008, and then obviously I just got my master's.
And I'm Michael Reimold. Also worked with Kevin for many years in my career, and also have 13 years of industry experience in basic design. I go back a little bit further with software. That was kind of what I got into in the beginning, as you can see. And I'm also working on my master's degree as well. Just about.
Yeah, we're gonna get him graduated here soon. And we found a friend over at the University of Louisiana Lafayette. I'm sure you guys are familiar with this guy, Boise. I don't know if you want to say anything. No? Shy? All right.
He doesn't have a microphone.
But this is an example of the community support that we received from the CoCo community. You guys really kept a lot of not just documentation alive, but building new tools, new resources. Anything I needed, I could come in on Discord and annoy you guys and find somebody that can help. And finally, I wrote one in too. So, and Boise will actually be taking our IP, and he will be using it for a springboard for his PhD that he's working on. And this is his supervisor, Dr. Marmella. All right, so what are the goals here? So the goals are that we want to build a open source professional microprocessor IP. So over here, we have a SoC. So when Apple or whoever presents their latest smartphone, they always talk about, oh, we got this 10 billion transistor mammoth of an SoC. Well, what is an SoC? An SoC is basically if you take like the CoCo had a PCB with a CPU and I/O and these other surrounding parts. If you take that and basically put that onto a silicon die, you're basically integrating all these parts onto a system on chip, right? So that's the trend today, is to basically put as much as you can, integrate as much into one chip. And so typically on these large chips, you have a dual core or a 4-core ARM processor, so 64-bit, 34, 32-bit massive application processor, right? So that's not what we're trying to build here. What we're trying to build is a small, efficient microprocessor for subblocks. So, for example, in this particular SoC, there's a lot of other blocks in the SoC, for the I/O, display, GPU, a NAND flash controller, a USB, and these blocks often need a certain level of high-level control. And so it's not uncommon to want to place a small microprocessor in there to do such things as, I'm getting ahead of myself here, but to do such things as, controlled design for tests, to actually test the chip when it's fabricated, make sure it works correctly, manage a interface, or to actually be part of a controller. So that's what we're targeting here. So think of compact, think efficient, think different, okay? And I just kind of spoke about this, but here again is an SoC, and so here are all the possible places where you could place the Turbo9 IP. So this would be an SoC example now in the mixed signal ASIC, so that would be like a sensor. That would be like some kind of chip that would have some kind of sensor. Maybe it's some kind of audio chip or something like that that needs to have some high level controls. So that would also be an application for this. Now there are open source IPs out there that do this, but a lot of them are based on like a 32-bit ISA, like a RISC-V or something like that. And my argument is that's the wrong choice. You don't need, if you don't need 32-bit precision, why are you using a 32-bit processor? You're just going to waste memory and area. So my argument is let's use a 16-bit CPU and let's make it as efficient and as high performance as possible. So that's basically the premise of my thesis. So there's a demand for a compact and high performance 16-bit CPU with efficient memory utilization. So we have to choose a instruction set. All right, so this is where I intersect with the 6809. So we could design our own instruction set, but if we can design our own instruction set, now we gotta write the assemblers, the compilers, and all these other tools. We have to write those, and then we gotta convince people to use them, right? And there's no code base out there. So it's better to choose an existing ISA, instruction set architecture. That's basically the instruction set spec of a microprocessor. And then you can borrow all the tools and everything that you guys are already using. But then the other requirement is that at minimum, we want to run C code. And we want to run C code at a decent, performance level. And the 6809 really stood out because, it has these excellent addressing modes. Like, for example, you can do stack relative addressing. You can do indirect addressing, that's like pointers. So it actually fits quite well with the C compiler. Now, the 6809 instruction set is not RISC, right? Today, everything is RISC, right? RISC is wonderful, blah, blah, blah. Well, if you use RISC, what you end up with oftentimes is a lot of internal registers, right? So if you look at these RISC processors, they have like 32 internal registers. If it's a 32-bit processor, now you have 32-bit internal registers, 32 of them, and that comes down to die area. So registers, flip-flops are actually very area, they take up a lot of area, so that's going to just grow your die size quite big. So you want something with minimal amount of registers, and again, the 6009 fits well. The other thing is the design of the ISA is very elegant. I don't know if you guys have read Terry Ritter and Joel Boney's article in Byte Magazine, but he kind of covers it quite well there, is that it was a clean slate design. They took the 6800, and of course the 6502 was basically kicking their ass at that point in time. And they took the 6800 and they analyzed the code and they said, okay, let's what can we do to improve this? And so it's not binary compatible with the 6800, but they made it source code compatible, and they added very nice addressing modes, and they were able to combine some of the instructions into one instruction. And so basically, it's a very nice, clean, orthogonal design. So, but it's a CISC microprocessor, which basically the only rule it really breaks is of the RISC versus CISC rules is that it breaks the load store rule. So in a RISC design, you typically load your data, you then add, subtract what you want to do, and then you store it back. Whereas in a 6809, one of your operands can actually be memory, right? So it's A plus whatever this memory address is. So, but we want to go high performance. So we have to build a CISC to RISC pipeline microarchitecture, which is not something you see in the literature really anywhere. So that's what my thesis is on. Now we want this to be professional level IP. Okay, so what does that mean? So you guys gave us all the assemblage compilers and existing code base. Thank you very much. But when we do this design, we want to use modern RTL design techniques. RTL is basically an acronym which is Register Transfer Language, which when you're coding in Verilog or VPHDL, it's the subset of the language that can actually be synthesized into gates. Please ask me more questions if you have any. So we're going to use modern RTL design techniques. We're going to use a modern SoC bus. So the bus that we use is the Wishbone pipeline Wishbone bus. So like it's an open source standard where other people can develop peripherals and stuff like that adhere to the Wishbone standard. They can easily hook it to the Turbo9. And then we're going to also analyze and optimize for speed, power, and area. So that's, as an IC design engineer, those are the three trade-offs that you're always trying to balance. You have to decide which one you're aiming for. And then we're going to do a full verification test bench. Now that is a very unappreciated part of this. That is a full test bench that takes the Verilog code, adds behavioral Verilog code, just like C code, and actually stimulates the design and then tests its output. That's what Mike did a lot. All right, so I'm going to go very fast here because I'm going to try to get you guys really deep down in the weeds. So some of you guys have probably seen my YouTube presentations, so you probably have seen a lot of this. I really want to get you guys to the parts where, it's like the Matrix. So this is the microarchitecture details. So at a high level, we have a fetch stage, a decode stage, an execute stage. We have a Wishbone controller, and that interfaces out into the external memory. Externally, we are on Newman. That means that we have a shared program and data space. But internally, we have what's called a hardware architecture, where a separate data bus and a separate program bus. And this Wishbone controller basically figures out, what access is out there. Now, as drawn here, I think this is 6 pipeline stages. So 1, 2, 3, 4, 5, 6. So everything is pipelined not just in the processor, but actually on the memory bus itself. And this has to track transactions. So like if you say, if the fetch stage says I want to read, it'll basically send it here, that transaction will go out here, and then several clock cycles later, it will appear back here, and it has to know, oh, that was the read that happened 3 cycles ago, I better feed that back to the fetch stage. This is a more detailed view of the design. This is the fetch stage. I'm going to go very quickly here. It incorporates an 8-byte instruction queue. In some ways, it's similar to a cache. It's not really a cache, but it does have similar features where it's always trying to read ahead and trying to predict, where the next instructions are coming. Like I said, there's a pending transaction tracking to know, okay, I've sent so many out, and I'm expecting so many requests back. And then there's flush logic. So what has to happen here is that if there's a branch over here and I mispredicted the branch, it needs to know not only to flush this FIFO, but it needs to also ignore a certain number of transactions coming back. So that's what that logic does. Another thing to note is that this is not a traditional FIFO, which is a circular FIFO. This is a shifting FIFO, and then the reason we use that is because we want to present only registers to this side to minimize time impacts. This is the decode stage. I go into great detail on this later, but it basically translates 6809 instructions into crisp micro-ops. And we create our own microassembler, the microassembler that actually takes microcode and creates Verilog blocks that then create the micro-ops which execute the instructions. This is not old school microprogramming, so some of you guys might be familiar with old IBM mini computers and mainframes that used microsequencers and such. This is a step beyond that, and that's what kind of gives this the unique aspect of this as something that we're seeking publication on. This is the execute stage. I mean, it's a beautiful execute stage, but nothing really crazy. It's got a 16-bit ALU and a 16-bit address ALU in parallel. If you think of it as the 6809, it's an 8-bit implementation. So what Motorola made was an 8-bit processor that executed the 16-bit instructions, right? So it would take multiple cycles to do those. 16-bit words. But we're like, okay, well, we can do whatever we want. This is a totally different microarchitecture, so we're fully 16-bit, and we have 2 ALUs that we can do address calculations and data calculations in parallel. There's also a data memory controller, which in some cases acts as an extra pipeline stage as well. But we also add something called a sequential arithmetic unit. It's buried in the data LU because, so there's the multiply instruction on the 6809. I could have implemented this in microcode and done shipping ads to do it, but the way I was looking at it, I would have to create some tiny paths in my data LU I wanted to avoid. And so what I did was I created a little block in itself that can do these multiplies. And then I added some instructions on top of that. And I took from the HC11 and HC12 multiply instructions. The reason I use those and not the 6309 is because the 6309 relies on registers that the 6809 I say doesn't have. So I use the HC12 ones and the HC11s. And then there's also other possible algorithms that you can implement here, such as quartic algorithms to calculate trigonometric functions, cosine, cosine. And this can also be parameterized out. So when you synthesize the core, you can actually say, you can choose from the menu and say, I want to add these, or you can actually remove them all if you want to create a smaller, more compact CPU. And the other thing that we did is we have a full 16-bit data path, and I extended out this data path to be fully 16-bit. I extended this data path to be 16-bit. This data path can be 16-bit or 8-bit. You can actually parameterize that and choose that when you synthesize. And so what you end up with is a true 16-bit processor. It's a true pipelined 16-bit processor, and it has these extra multiply and divide instructions. All right, let's talk a little bit about outside the Turbo9. So this is the pipelined memory bus, how you would set it up. Now you can have, like I was talking about, you can parameterize these things. So you can have the Turbo9 in several different flavors. You can have the regular Turbo9, which is fully 16-bit inside, but it has an 8-bit external bus, which means that your 16-bit transactions will take 2 cycles. You have the Turbo9S, which is 16-bit internal and external, but whenever a 16-bit word would be unaligned, it would take 2 cycles. And then the Turbo9R, which is the fancy racing version, has 16-bit internal and external data paths. It can do 1 cycle transactions for any underlined or underlined. Looking here, this is how the Turbo9 is actually set up as far as the wishbone bus. So this wouldn't be familiar to you guys as far as how the 6809 bus works. So you actually have pipeline stages out here. Now the trick is that you can parameterize these out. So why would you do this? Well, as a designer, if you're building a really big design with lots of peripherals, your timing path, the decode logic here, the decode logic here, it can become your worst propagation delay, which is going to slow down your entire clock. So now you have to run the entire system at a slower clock. And so what you're doing is you need to balance the latency with throughput, right? Well, not throughput, but latency with absolute frequency. So you can just remove or add these registers here, reduce your latency down, and if you're happy with your clock rate, then you can move forward with that. But sometimes if you add latency, you end up with a higher frequency, and you actually have higher performance. So it's a tool that we give to the designer. All right, now I'm here to where you need to be. Well, I got you to where you need to be. Morpheus is here. Says, let me show you how deep the rabbit hole goes. You guys ready for this?
Yes.
No one word. You don't want to go back. You don't want to go back.
Take the rabbit hole, guys. Let's go. All right, so I'm going to give you some microprocessor design background. So, like I said, the Turbo9 is a pipeline design, but the 6809 is a multi-cycle design. So, when you read that data sheet, it says, okay, this instruction is going to take X number of cycles, right? So that's because these guys, each one of those cycles, it implements a step to execute that instruction. So what I'm going to show you here is not actually a 68, like a Motorola 6809. This is a theoretical multi-cycle 6809. And what this is essentially the same execute stage, the same data path, so it has the same 16-bit capabilities as the Turbo9, but I'm going to implement it with a traditional controller. So it will be faster than the Motorola implementation, but I'm using this as an example. And here is a state diagram on this particular multi-cycle 6809 example. And I'm taking the add instruction. So this should be familiar to you guys. This is an opcode matrix. So here is the most significant nibble. Here is the least significant nibble of all the the first page on opcodes of the 6809. And you can see here that our friend Terry and Joel did a nice job laying these out in a systematic manner. You can see that all the add instructions here, add A, add B, and add B, and then all the immediate direct index extended, and they should relate to this diagram down here. So we're just taking all the added in instructions as an example, and so in order to do this in a multi-cycle design, you have a fetch state, an eco state, and then you would break out into whatever addressing mode you have. So you have all the 8-bit addressing modes here and all the 16-bit data addressing modes here. The 8-bit addressing modes, immediate, direct, index, extended, and then index can also go to the indirect feed into the add A and add B micro states. And then likewise, we have the 16-bit versions up here. Does this make sense? Okay.
Yeah.
So this is 15 total states, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So you need to have a state machine that implements 15 different states in order to do this. Your fastest path through this would be 3 seconds. 1, 2, 3, 4, and then back, and then whoops. The other one would be 1, 2, 3, 4, 5. Okay. So it's going to take you 4 to 5 cycles in order to execute any one of these instructions, and you're going to need to have a state machine that has 15 states. All right, so you could create this controller. Let me back up. I didn't hit this. So what we're talking about now is this state machine here, which is going to implement the control vectors. These are control vectors, which basically control the ALU and select the register in order to implement these instructions. So now we're going to talk about how to implement this controller, the thing that's going to create these states. So you can take the classic version, right, which is just a state register feeding into some logic. You have the next state feeding back to determine your next state. You have some inputs and some outputs. This is not a microprocessor state controller. This is just a simple state diagram to prove a point. So here you have the state diagram, state go, goes into state A, checks that the input A is 1, it goes back here, and it sets the control vector, which is your output to control whatever you're controlling. Make sense? All right, now let's introduce you to your microprogram state machine. Okay, so this is what they started to do in the late 60s, 70s, where they were building these mini computers and mainframes. They would instead of doing it with random logic in a traditional sense, they would use a ROM, right? So you have microcode sits in a program ROM, and you have something called a microsequencer. So these were off-the-shelf parts that you could buy back in the day. They were made by AMD, Atmel, Texas Instruments, and they basically can implement the same exact state machine. And what you do is you have, this is essentially the state register, and then that feeds the address of the ROM, and then the output of the ROM is split up. So you basically, here's the microprogram word, and we're going to slice it up, okay? So the first 2 bits are what's called the microsequencer operation. This is the conditioner select, this is the branch address, and then the control vector is what's going out to your data path to control your ALU and all that kind of stuff. But what this does, the micro op can actually select, have little micro operations, like it's essentially continue to the next state, or branch, or take the branch address and jump somewhere else in the microcode, and you can make all that stuff conditional as well. So if input A is true, then branch over here, right? So we're down on state 2 here. If input B is true, branch back up to state 0. Make sense? So this is all pretty classic stuff. Unfortunately, this is not showing up very well, but so this is the microcode. Now this is actually the language that we developed, right? So this is Mike built the microcode assembler, and you can see here that we have these states as we showed before: state go, state A, B, C, and N. And we have those same decision points. We have like a jump if A, go to state go, so on and so forth. And then how this works is that all these mnemonics are defined in a macro file. And the way you read microcode is different to what you're used to if you're used to 6009 assembly. 6009 assembly, typically one line equals one instruction. In microcode, whenever you see in our microcode, whenever you see this keyword called end state, that means that the microcode assembler is going to assemble everything and create that one microprogram word. So all these are macros, which then set these control vectors in the microcode ROM, and then this gets compiled into that state. And these mnemonics are defined in a macro file. And the reason why we do a macro assembler, because we don't actually need to do a macro assembler, is that we developed this in parallel. So Mike is sitting there writing the micro code assembler while I'm doing the hardware design. And if I'm changing like some control vector, I don't want to have to go back to Mike and annoy him while he's working hard. So I can just change the macro file to just basically define how my hardware works, such that Mike can keep working. So, all right, so we covered multi-cycle processors, we covered traditional state machines, we covered microcoding techniques. Let's talk about pipeline microprocessors. So what a pipeline microprocessor does is it overlaps multiple instructions. It's a form of superscalar execution. So what's happening here is you have three instructions, right? So they could be any instruction, but you have a fetch, decode, and execute, right? And you're overlapping the fetch of instruction A, and you're overlapping it with the decode of instruction B, and you're overlapping the execute of instruction C. So you're essentially processing three instructions at the same time. From the software programmer's viewpoint, this just looks like faster throughput. So effectively, you're getting, if these were all one cycle in instructions, you're getting a instruction completion every single cycle, even though they're actually taking 3 cycles to complete. You're doing it in parallel. And you usually see pipelined microprocessors implemented for RISC, because RISC is a RISC instruction set is actually written with pipelining in mind, right? So they want to reduce data hazards or control hazards as much as possible, and that's why they do that load store architecture. So CISC is not the ideal case, but we're going to make a CISC to RISC translation layer. I don't have my pieces here, but it's fine. I'll wait. And this is something similar to what Intel did around the 486 or Pentium. At the 386, they were still a multi-cycle, design where they would take multiple cycles to execute one instruction. But the 46 and Pentium, they basically started to break down and pipeline the micro operations to get more throughput. So that's what we're doing with the 6809. So here is a picture that took me a week to draw. This is a very detailed look at the decode stage of the Turbo9. And this is where we start to get into the uniqueness of our design. So you see some stuff here that you're familiar with, right? So you see this thing called the microsequencer. We'll talk about that. We've got the microcode. We're not calling it a ROM now. We call it micro-RTL. We'll explain that later. We have something that's called the instruction pre-decoder. Okay, so here's the fetch stage with that queue that I'm talking about, the instruction queue, and it feeds into the instruction pre-decoder to do some basic decoding right after that. Figures out what the pre is. There's a pre-byte, and a post-byte, and it basically says, okay, you're on page whatever, and this is the opcode, feeds into these magical blocks up here that we'll talk about in a second. And then also the post-byte, we route that directly to the stack and index addressing mode of decode, because it's if you look at the post-byte, it's very well structured. That definition of like, okay, if you're in stack addressing or index addressing these bits, do this and so on and so forth. You guys know this. And then there's also some miscellaneous stuff down here that to determine, okay, if this is an index instruction, what is the branch? So like, if you have a branch instruction, what's the condition codes I need to look at for the branch, so on and so forth. The other important thing is that this also pulls out the immediate data. So if you have a load immediate, right, a load immediate, it'll pull that data directly out. This is stick it right here. What is this? This is a register, right? So in a pipeline processor, you have a register sitting on your boundaries. This is the register that sits between the decode stage and the execute stage. And this essentially is a RISC instruction. Okay, it's a very wide RISC instruction, but it'll obey all the same rules as a RISC instruction. And then, so that leaves us only with these special blocks up here. And I don't want to go into too much detail on this slide, but I will just point out what's happening here. So we have these control vectors here. We have data ALU A, data ALU B, and data ALU write select. And what that says is that you've got this ALU, right, in your execute stage, and I want to put this register on this side of the ALU, I want to put this register on this side of the ALU, and I want to write back to this register. And so what these are doing is they are merging with the control word from the microcode, and you're basically pulling which register you want to operate on out of these decode tables. That's where we start to get into magic. So Mike here wrote the microcode assembler from scratch in C. Why didn't you use Python?
Because I'm a C programmer.
I love it.
I use Python.
Yeah, I don't understand. I love Python. I had Python. I write C. Let's see. And
it was interesting to know that when we were developing this, that we didn't really have a language fixed at the very beginning.
Yeah.
So as I was implementing things, I started to run into these cases like, well, oh, this would make more sense if I had, if you had something that starts this type of block and ends it here.
Yeah.
So we came up, we agreed on how it's going to be written, how the implementation.
Yeah. Yeah, and I remember coming up with this unique part was like a epiphany at one point. I was like, we could just use decode tables.
Yeah, because we started out just generating the decode tables,
and I basically, I went and like started writing I rewrote all the microcode, assuming like some syntax that we just agreed on, and you went and basically wrote the microcode assembler to create these things here.
And actually, the way I wanted to implement this was different than the way you had it in mind. Because I was going to make everything into these linked lists and have everything pulled together. And then I wasn't really explaining to you what was going on, and then just kind of fell out.
Yeah. So unlike the classic microcode assembler that we showed earlier, this outputs not only the microcode, but also these decode tables and these control vector statistics. And they don't actually output along, so they're actually outputting straight Verilog. And the reason we do that is because we're able to optimize the controller down so efficiently. It's actually optimal to just compile it, just synthesize these gates not along. And so here's an example of those three blocks. So now your microcode becomes a Verilog file, and it's very simple, really, and that's a good thing. So basically, it's just a big case statement, and so you're breaking things down into very simple chunks that synthesis tools love, and you just really crank it down. And then you have your decode tables, and so I wish I could show it more. Do I have the deployment version of that? So basically, let's just go back to what kind of decode tables we have. So we have like this what's called the R1 register pointer, and the R2 register pointer, and the AR register pointer. So this is an address register pointer. This is R1 and R2. So what happens is that we can use pointers now. So we have pointers to registers. So now, if we go back to the add instructions, we have add A, add B, add D. I can implement all three of those in instructions with one micro op and just refer to R1 and R2, and those will be decoded off the opcode directly. So I don't have to have multiple microcode states, which is what you typically do in a microprogramming machine. In addition to that, you have the jump table A and jump table B. And what that does is it creates a directed vector into where you need to be in the microcode. So say you're basically finished with the last instruction, you're ready to fetch and execute the next instruction. Well, obviously it's already fetched, and you basically just point to the jump table A, and it will vector you directly to where that next piece of microcode to implement that next instruction is. So there's no extra cycles needed. And so these are two Verilog blocks, but then we also have the control vector statistics. So Mike's code, he's building these big old linked lists, and I asked him a favor to basically output these statistics on all the, not only the microcode, but also the decode tables to give me statistics on how I'm using these. So in the entire instruction set of the 6809, I can say, oh, on the R1 decode table, I seem to be using A 55 times, I'm using B 54 times, I'm using the program counter this many times, so on and so forth. And that allows me to then change the encoding or optimize things. There's ways I can look at this and say, oh, well, I can change my hardware to be more efficient. Here's the data ALU operation. So this is the operation that the data ALU does. Obviously, I do a lot of A plus B, so a lot of adding. But that's because we use add to actually pass data through the data ALU, because we just add 0 to it. So this is a pretty standard ALU. A plus B, A plus not B is for subtraction, left shift A, right shift A. Now these A and B are not the A and B registered in the programming as you think of it in 6809. These are just the A side and the B side of the ALU. Then the logical functions and or XOR, and then this is the sequential arithmetic unit gets piped in through there. So now let's look back at this at the opcode matrix. So this is just taking the R1 register pointer, for example. And so you can see here are all the instructions that use the A register. Here are all the instructions that use the B register, so on and so forth. And so there's definitely some regularity to how they encoded these in instructions, and it's to your benefit to not put this in the microcode, but to decode it directly off the opcode. Because when you decode it directly off the opcode, the synthesis tool loves this. It's like, oh, well, I can just take this whole block and minimize my logic. Whereas if you were coding it off the coming out of microcode, you would be associated with some address of the microcode which has nothing to do with this. So this is an extremely important point to allow us to make this design as efficient as possible. Here's some more jump tables for the other one. If you go to our booth, I have my full thesis out there. You can refer to all the appendix, all this beautiful color. And so here's an example of the microcode to do the add-in instruction. So this is one piece of microcode. Okay, this is one state. So here's your end state, and everything here will be compiled into that micro op. And so we have data add R1 plus R2, data write R1. This looks very brisk, doesn't it? And then we set the data width to whatever R1 is. So we're saying, okay, if R1 is a 16-bit register, make sure that you're using the 16-bit functionality of the CCR and the ALU. If it's 8-bit, use 8-bit. And then we set the CC, this is the CCR op, which is just, don't worry about it. It's just the way I was able to encode which bits get set. Then we have jump table A, next PC, which basically means I want you to go to the next position in the next PC. You tell them that to the fetch stage. You say jump table A, which means I want to go to the next microcoded address for the next instruction. And so that's pretty self-explanatory. And then these are the unique parts of our microcode assembler. So these are the parallel decodes. So when you're doing microcode, you do a lot of sequential states. This is how you basically say, okay, I want to do some parallel decoding. So you see here, this is jump table A add. Add for add A. We're going to set that to this label here, add. So all these are basically setting the jump table A to add. Now there's jump table B also being set to add. So you notice all the immediate instructions will jump immediately to this piece of microcode, whereas all the ones that have an addressing mode, direct, index, or extended, will go somewhere else by jump table A and then jump down here to execute the next thing. So what that's doing is doing the addressing mode before it gets to this state. And then you can see here we're setting R1 to A for add A. We're setting R1 to B for add B and D and so on and so forth. Does that make sense? You have any questions here? All right. So now we can compare our theoretical multi-cycle 6809 to the Turbo9. So like I said before, this is 15 total states, and your cycle time would be minimum of 4, maximum of 5. Here is the Turbo9, and so let's just take an example here. Let's say that we've just finished executing an instruction. We're going to the next instruction. So we go through jump table A. Let's pretend that that's an immediate instruction. It'll just jump directly to that back to that microcode, and it'll execute the add immediate instruction in one cycle. Whereas you take another path, let's say you come back through here, and it's let's just call it an indirect, just to be hard. You'll go to the index addressing, and then it'll say, oh wait, this is an indirect. So if you calculate your index address, and then you say, wait, this is indirect, so you go to your indirect state, and then you go through jump table B back to your add microcode. So this is all the same piece of microcode. You're implementing all those instructions. It's a total of 4 states, so you only need 4 states to implement all these. And the minimum cycle count is 1, and the maximum is 3. So that's quite an improvement. And now this is my favorite table. So we got the Turbo9R going against our 6809 example, our 16-bit multi-cycle 6809 that were theoretical. And then we got the original Motorola 6809, right? And so lots of details, blah, 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 blah. Let's look at this number down here. So for all these different variations of add-in instructions, the original Motorola 6809 can do 2 to 14 cycles for any different variation. The multi-cycle 6809 can do 4 to 6 cycles, and the Turbo9 can go 1 to 4. So that really shows the performance advantage of the Turbo9 microarchitecture. Dry stone. So we got we implemented several different benchmarks in order to test the performance, because obviously I just explained to you the theoretical performance, but in the real world you have to run some kind of synthetic benchmark or whatever to impress people. So we chose dry stone. We looped in Boise, and he helped us out as well. So what we got here, we have a Motorola 6809. This is what's called performance per clock, or units per megahertz. The reason you do this is because if you were to implement the Turbo9, in an older FPGA, it would be slower than in a newer FPGA. Frequency scaling, right? Where you synthesize it in a 7 nanometer process versus a 180 nanometer process. The 7 nanometer processors will be able to run at a higher frequency. So DMIPS per megahertz basically takes that out of the equation. It just says, how efficient is your logic? You designed this processor, how efficient is it just on terms of your logic design? And so you see the original Motorola 6809 achieve a 0.18 DMIPS per megahertz, and the 16-bit 1 clock latency Turbo9R is at almost 0.7. We compared it to the Mega AVR, the Arduino processor, because that's a good argument against what I'm trying to do, is saying, well, why don't you just use an 8-bit RISC? Well, here's your 8-bit RISC. It's at 0.14. And then we also compared it versus the RISC-V. Now, there are RISC-Vs, obviously, that will run faster than this, but this is the Pico RV32 RISC-V, which is a common RISC-V implementation targeted explicitly for microcontrollers in an SoC. So we're beating them as well. They're at a maximum of 0.5. And now here's the raw frequency performance. So now let's take frequency into account, but all on the same platform. That's why some of these are missing, because I wasn't able to implement them on the same FPGA. But so we implemented all these cores on the same FPGA, so we're on even footing as far as frequency scaling, and we have the RISC-V versus the Turbo9. Now you see that the 2 clock latency Turbo9 actually becomes the highest performance over the 1 clock latency. Remember we talked earlier about balancing latency versus Fmax, right? And so this is a good example of that. So we're beating the RISC-V, PicoRB, RISC-V at 196 megahertz, and we're at 112 megahertz here, which is still outperforming. We also just provide the original 6809 here just for reference. So here's the one that whets your appetite, basically. If you just say, okay, you got 1 megahertz 6809 versus a Turbo9 at 112 megahertz, what's the equivalency? So it would basically be the equivalent of running a 337 megahertz 6809. Also note that if you put this in an ASIC, right? So if you fabricate this directly into silicon, right, we would be touching over a gigahertz. Now you got like a 3.7 gigahertz 6809. All right. So the competition, let's not waste too much time on this slide, but kind of talk about some of this stuff. But just to give you an idea, an ARM Cortex M0, which is a commercial solution for embedded microcontrollers, that has a EMIPS per megahertz of 0.9. So we're at 0.7. I got a couple other tricks up my sleeve, some branch prediction. I'm going to talk to a certain compiler writer to help me out with maybe a custom instruction or not. But the main thing I want to put here is like, look at the memory bandwidth. So, you know, the original Motorola has 8 bits of memory bandwidth. That means on every clock cycle, you can move 8 bits of data across your memory interface. Turbo9 obviously has 16 bits. But, and that Mega has 24 because it has an 8-bit data bus and a 16-bit program bus. And then some of these RISC have up to 64. So, I mean, that just shows the efficiency. So you're basically moving these highly encoded instructions over this data bus, and you're able to achieve these levels of performance. And obviously, we're an open source IP, and then there are, you know, some clones available for that Mega and the Motorola, and there's open source for the PicoRB. I want to just note something. We had a live GitHub at the beginning of this project. We had to take it down temporarily because there's, you know, certain, you know, colleges and whatnot involved, and we're basically making sure that we do everything by the book to make sure that there's no claim, legal claim, and we want to make sure that we get that out in the open source, and we are making progress on that. So we will turn that line again soon. But you can come out of my booth, and I'll show you the code. It really exists. The benchmark overview. Okay, let's accelerate here. You know what Drystone is. ByteSim is an old prime number sorting algorithm, and we chose that because we could write it in C and assembly, and it was small enough to where we could port it across platforms. Comparing C compilers, we looked at GCC, CMOC, and DECC. Of these, DECC was the fastest. It's written by Dr. Volker Barbarken out of Germany. And he was very helpful on this project, and he actually made a targeted port for the Turbo9. So we have our own compiler that implements the extensions, the multiply and divide extensions. Let's see, yes, what we talked about. Welcome in a bit here, Drystone, we looked at code size. Obviously the Turbo9 has the smallest code size. There's AVR, there's ByteSim. This is an example of, we have the smallest code size for ByteSim and C, ByteSim and assembly. So with this, me and Boise had a little fight. He wrote all the assembly for RISC-V and AVR, and I wrote the assembly for Turbo9. We reviewed each other's code. We argued over what was legal and what was not legal. We came to agreement, and we're both happy with Turbo9. So the performance, in terms of assembly, we are faster. In terms of C code, we were actually slower than AVR. I'm not ashamed of this. If you look at the AVR GCC compiler, it is one hell of a good, mature compiler. So we have a little bit of compiler optimization there. So this is the AVR and C, this is the Turbo9 and C. So we just need to get some compiler optimization there. But in terms of assembly, we beat the pants on AVR. Let's talk about area and power. So at the time of writing my thesis, I hadn't gotten to synthesizing into, I want to synthesize into a real IC, and I give you like the 2-input NAND size, right, to actually look at transistor size. So this is FPGA resources. So FPGA, looking at area, can be a little bit more confusing because in FPGA you have what's called lookup tables, LUTs, and you have flops. So you have these resources, and they don't map exactly one-to-one with so many NAND gates. Okay, the algorithm doesn't it's not simple like that. So anyway, compared to the Pico RB, which is the 32-bit version, they were a little bit smaller in terms of LUTs versus the Turbo9, but we beat the pants off them in flip-flops. So if you look at it overall, if you look at the raw transistor side, it'll definitely be smaller once I go to the IC thing. But you got to look at the performance. You're only getting 0.2 dB per megahertz out of this Pico RB, whereas you're getting, on the 8-bit version, you get to 0.4, 0.7 on the Turbo9. And then for this was the one that had 0.5 dBs, which still isn't beating the Turbo9R, and it is much larger. Look at how many, flops are massive. Flops take, 20 or 30 transistors to build. So once I get the ASIC numbers out, we'll basically show you that it's much smaller. Also, in terms of power, if you can run something slower and still achieve the same performance, and you have smaller area, that means you have less capacity for charging and discharging, which also factors into power. For IP development, we were using Cadence tools. We switched to open source tools just because we like open source tools. Mike wrote the microcode assembler. We use GTK Wave, and right now we're using Silence tools. We will be using Biosis. Also want to mention, we use William Maskell. Sorry, I'm going to mispronounce that. Assembler extensively. So here's the verification suite. Mike, you want to talk about this?
Yeah, so we set this up, we had like a assembly program that we put together that would let's get this going.
So the top level, let's talk about top level.
Okay, so if you just want to go from the slides, so basically what we have is a way of setting a program into both the actual Turbo9 RTL and into a behavioral model.
Yeah.
And they should do the same thing. And then on the output side, you can just be comparing the results back, and if it matches them, you have a passing ISA instruction. It's not complete until you do randomization. That's why you have 24-hour regression. Constantly randomizes the data that goes in, and given the sheer number of all the different addressing modes and everything comes together, 4,500 attributes.
Yes, it's all the combinations of
It's all combinations of everything.
each instruction, each register, each addressing mode.
Self-testing and covers the full ISA. And as I just said, it had fully randomized inputs.
And it runs the matrix.
Yeah. And all those attributes fit into 34 separate test cases.
Yeah. So this is like a whole other model that we built. This is like an emulator. So this is written in Verilog, but it's a whole other 60 or 9 that can't be synthesized. Yeah, but they can be used to check to make sure that this is working right. So you basically feed it the same stimulus. You basically come back and you check to make sure it matches. So here's a kind of the status of where we are in terms of verification.
Right. So I think what's left, because almost everything's in here. It's just a handful of instructions.
I have not finished the interrupts yet. So pretty much everything is verified and tested, except the interrupts because I haven't done yet.
And the jump.
Yeah. Some of the stack instructions. They're there, but those are not tested.
They're implicitly tested, right? Because they're being used.
Yeah, they're being used, but they're not. Yeah.
They're not actually under test.
Yeah. There's a difference between using an instruction and seeing if it works versus like beating the shit out of it. Okay. Every single combination. Sorry. So here's kind of the software tools that we use. So we're just looking at a source code here, and here we're using the VPC compiler. But we can feed this into 4 different platforms. So like we said before, we have this behavioral model, which is like a 6809 written in behavioral Verilog. We have the Turbo9 and RTL. And then you can also feed it into the Sim6009, which for some of you guys are familiar. We took that code and molded it a little bit to make it friendly to our design. And then you can also feed it into an ASIC, and all these run the bootloader, which then can be run across all platforms. So you can actually take the same piece of code and you can simulate it and get your console output, or you can run it on real hardware and get your console output, and then you can also drop it into waveforms too. And the summary is blah, blah, blah. I graduated already, that's the summary. Thank you. Yeah, so the question is, you say this, you go ahead, this.
The Turbo9 is the processor solution for compact, high-performance application where size and efficiency matter.
Acknowledgements. Obviously, I won't go into too much detail here, but my family and Dr. Lynch is the guy that was in my undergrad who got my brain started on my process design. Terry and Joel Boney, I've actually spoken to Terry a couple times. I invited Terry to my master's events and he attended. That was fun. Yeah. And you guys, I've annoyed a lot of you guys, and I really want to say that you guys have embraced me and you have helped me whenever you can, and you provided all these tools, and I really appreciate that you guys kept that alive and made my job easier. So thank you.
Thank you.
Good.
Any questions? I think we're gonna roll over. I don't know if we can roll over a couple minutes. Go ahead.
So I saw your table, but no one's there. I guess I found you guys doing presentations on planning. Anyway, so sort of similar to what I did in college.
Right.
There's a lot of fields.
Awesome.
It's a career field. I should say that. Anyway, the question I wanted to ask was, I didn't see the whole main part of the presentation. You mentioned that in my so I assume they're doing just a regular scanning.
Yes.
Assumptions.
Yeah.
Basically, is it comparable to like what the work is doing?
Yeah.
So is it basically a similar approach you did for this?
Yeah, I can't speak to exactly. I've read the paper from the 46. I can't remember what they did, but yes, we're using static range prediction at this point. So we just assume that. So there's two program counters. What he's talking about is that the best stage is a program counter and the extra stage is a program counter. The effects stage basically has a program counter that just assumes that it's going to keep going in a straight line. It doesn't know anything about what it's loading.